Approximately 50 humanoid robots performed synchronized martial arts at the Temple of Heaven in Beijing. This wasn't a lab demonstration or a closed stage performance. It was a public display at one of China's most historic cultural landmarks. Robots executing flips, kicks, and coordinated patterns in perfect synchronization. The immediate question is whether this is just choreography or evidence that China is scaling humanoid robotics faster than anyone else. Unitree had previously displayed similar cluster control capabilities at the Spring Festival Gala, showing that this is a reproducible, refined system that the company has been perfecting over multiple public demonstrations. What's important to understand is that this was not remote joystick control of individual robots, where an operator would be manually steering each unit like a video game. Instead, it was coordinated execution across 49 robots operating simultaneously through a unified control architecture. Each robot received pre-programmed motion sequences that had been carefully engineered beforehand, but the system also provided real-time posture correction. This required a centralized choreography engine that defined the motion sequence and timing for all robots, time-synchronized motor commands, where every robot received its commands at precisely the same moment to maintain synchronization, local feedback correction where each robot sensors fed back information about its actual posture and balance, allowing the robot's onboard computer to correct drifts autonomously in real time. What this demonstrates is that Unitree has engineered a system capable of coordinating dozens of complex electromechanical units simultaneously. The robots in the Temple of Heaven performance were identified in reporting as Unitree's G1 humanoid robots. Unitree's G1 is a smaller humanoid platform that weighs approximately 35 kilograms, making it one of the more practical options for dynamic movement and acrobatics. The G1 features 23 degrees of freedom as a standard configuration, with higher DOF configurations reaching up to 43 degrees of freedom depending on the specific options chosen for different applications. This range of motion provides what's needed for flips, kicks, and complex balance adjustments that we saw during the temple performance. Rather than using hydraulic systems, which would be heavier and harder to synchronize, the robots include integrated IMU sensors, which are inertial measurement units that detect orientation and tilt in real time. These sensors are absolutely critical for the balance correction we saw during the dynamic movements, allowing the robot to sense when it's beginning to tilt and make corrections before it falls over. Additionally, the robots have vision systems consisting of cameras and depth sensors for environmental awareness and foot placement. The structure itself is lightweight aluminum frame with carbon fiber components, keeping total weight manageable while maintaining the structural rigidity needed to support the forces generated during acrobatic movements. What's strategically important to understand is that Unitree is one of the few companies globally that is shipping humanoid robots at scale. Most Western humanoid projects are still in limited production or pre-production phases, producing only a handful of units per year. What's crucial to understand is what this system is not. This is not artificial general intelligence. The robots are not thinking or learning during the performance in any meaningful sense. It is not adaptive autonomy in the sense of the robots responding to completely unexpected obstacles and deciding what to do about them. It is advanced motion planning combined with real-time control theory. These are the same engineering fields that power industrial robot arms in factories, making them perform repetitive tasks with high precision, but applied to humanoid platforms that must maintain dynamic balance while moving through space. The impressive part is not the artificial intelligence, it's the system's integration and coordination. The achievement is coordinating 49 electromechanical units with sufficient precision that they move in perfect synchronization while maintaining dynamic balance during complex acrobatics. This is the core comparison, and it's essential to understand that China and the West are pursuing humanoid robotics with fundamentally different strategies and different optimization goals. The Temple of Heaven event involved 49 robots performing in a public landmark, not a closed research lab. This is a strategic choice about how to demonstrate capability. China's approach also focuses on industrial scaling, where the goal is to optimize for production volume and cost reduction. Unitree is not primarily focused on pushing the absolute limits of what a single robot can do. They're focused on making robots that are good enough, reliable enough, and cheap enough to manufacture at volume. That's evident in their lower unit cost compared to Western platforms and their higher production volume ambitions. Unitree is one of the few firms shipping humanoids in non-trivial volume, and its leadership has publicly discussed aggressive shipment scaling targets. This happens partly because China's robotics industry benefits from government support for manufacturing and research and development. Even Western outlets covering the Spring Festival gala demonstrations described the jump in coordination and capability this year, and reported Unitree discussing large production ambitions for coming years. In contrast, the Western approach follows a different path. Boston Dynamics, owned by Hyundai, focuses Atlas on extreme mobility. Their robot can perform parkour, running, jumping, vaulting over obstacles, and navigating highly unstructured environments in ways that are genuinely impressive from a motion control perspective. However, Boston Dynamics produces very few units annually. Atlas is not a mass market platform being deployed across dozens of locations. The production numbers are in the dozens per year, not hundreds. Tesla's Optimus is focused on factory automation, where the goal is to deploy robots in Tesla's own factories and eventually sell them to other manufacturers for repetitive manufacturing tasks. The emphasis here is on industrial autonomy and task reliability, not on spectacular public demonstrations. The key contrast here is instructive. China shows scale and spectacle. 49 robots synchronized in a public landmark is an attention-getting display that proves manufacturing capability and systems integration, and other Western companies pushing the boundaries of what a single robot can accomplish and learn. These are not the same goal. China is optimizing for more units, coordinated large-scale systems, and manufacturing volume. The West, or at least the leading Western companies, is optimizing for deeper autonomy per unit, handling complex, unstructured tasks, and solving harder problems even if that means fewer units and higher cost. If you're building a factory automation system where robots need to work together on assembly lines, China's approach to cluster coordination and mass production is valuable. If you're exploring how a single robot can navigate unknown terrain, handle unexpected obstacles, and make complex decisions, the Western approach of pushing single unit capability is ahead. These robots can perform dynamic balance during complex movement, executing flips and kicks while maintaining stability. They can coordinate movement across multiple units, keeping dozens of robots synchronized while moving. However, there are significant limitations. They cannot navigate rough, unstructured terrain independently. The temple performance was a controlled demonstration with planned choreography, managed spacing, and a predictable performance area, even if it was outdoors rather than a TV studio stage. These robots are not built to climb over rubble, navigate forests, or handle truly rough ground. They cannot operate for extended periods on battery power. The robots during the demonstration likely ran for 15 to 30 minutes during the performance, which is a manageable duration for a public event. Military applications would require 8 or more hours of continuous operation, and the current battery and motor systems don't support that without significant redesign. They cannot make tactical decisions. The robots follow pre-programmed choreography like dancers following a script. They cannot adapt to unexpected situations or make strategic choices about what to do when circumstances change. They cannot survive battlefield conditions. There's no hardening against impacts, dust, sand, water, or electromagnetic interference. If the communication system between robots is jammed, spoofed, or disrupted, the entire cluster fails immediately because they depend on synchronized control signals. Military robotics today relies primarily on different platforms entirely. The military uses drones for aerial reconnaissance and strike capability. They deploy ground rovers, tracked or wheeled vehicles for transport and explosive ordnance disposal. They're developing autonomous vehicles for logistics and supply transport. Humanoid robots are not optimized for any of these roles. A humanoid is less stable than a four-legged platform on rough terrain. It has less cargo capacity than a rover. It drains its battery faster than a specialized ground vehicle designed for efficiency. Humanoids are generalist platforms, not specialists, and military applications typically demand specialist platforms because they need to be optimized for specific roles. However, there is long-term dual use. If humanoid robots improve significantly in certain dimensions, military applications become plausible. If robots achieve substantially better endurance, operating 12 or more hours on a single battery charge, if they develop genuine autonomous navigation capability, making intelligent decisions about where to go and how to get there without constant centralized control, then military applications become realistic. The critical distinction here is timing. Most military robotics experts assess that meaningful deployment of combat-capable humanoids is 10 or more years away at minimum. Current platforms are research grade. They're not designed for durability, reliability, long-term operation, or truly independent decision-making. If China were actively developing military humanoid robots specifically for combat roles, we would see different signals. We would see hardened platforms with redundant systems for critical functions, long-duration power systems engineered specifically for military endurance requirements, hardening against electronic warfare. Instead, we see public demonstrations of civilian platforms. This suggests the focus is on commercial and industrial applications, not military deployment. China has a mature actuator manufacturing base that has been built over decades of electronics and industrial development. Electric motors, servo drives, and gear reduction systems are not cutting-edge or rare. They're commodity items in Chinese industry. When Unitree needs 500 electric servo motors for a production run of 100 robots, the supply chain is domestic and established and cost-optimized through massive scale. When Western companies need the same components, they either source from China or design custom parts at higher cost and longer lead times. This creates a fundamental economic advantage. The motor supply chains themselves are globally significant. China dominates global motor manufacturing at the mid-tier level. Companies like Maxon from Switzerland and Harmonic Drive from Japan are world leaders in precision actuators, but China has scaled mid-tier motor production to enormous volume. This isn't about quality being worse, it's about scale economics. When you're manufacturing tens of thousands of motors per year, your per unit cost is lower than when you're manufacturing thousands. Rare earth elements are critical for high-performance permanent magnet motors, and China produces approximately 70% of global rare earth elements. This gives Chinese companies a cost advantage and a supply security advantage. Electronics integration is another layer. Semiconductors, circuit boards, sensors, all the electronics that go into a modern robot can be sourced domestically or manufactured in-house by larger Chinese companies. Government industrial support is a factor that matters strategically. China's government subsidizes robotics research and development through various programs. This reduces the financial pressure on companies like Unitree to achieve profitability immediately on every product. In contrast, the Western approach follows different constraints. US companies often prioritize high research and development investment because they're trying to solve harder technical problems, combined with lower volume production because the market for robots is still developing. Boston Dynamics, Tesla, and Figure AI are all pursuing high capability designs that require substantial R&D. They're willing to accept higher costs per unit because they're solving genuinely difficult problems. If Unitree can manufacture 500 humanoid robots per year at $50,000 per unit, the cost of a 100 robot cluster is $5 million. The cost differential doesn't just affect unit economics, it compounds across clusters. This doesn't mean Western robots are worse from a capability perspective. It means they're solving harder problems and willing to accept higher cost. But cost matters enormously for deployment scale. And that's where China's manufacturing advantage becomes strategically significant. Robot armies are not coming tomorrow to replace infantry. Humanoids are not infantry replacements in the near term. They're not going to be deployed en masse to fight soldiers in the field. That's not where the technology is or where the trajectory leads in the near future. Instead, a more realistic assessment is that military applications of humanoids become plausible only if several conditions are met. They would need self-healing hardware capability, continuing to function with damaged joints or sensors, rather than breaking down after the first impact. And they would need swarm coordination, where multiple robots work as independent agents that communicate and coordinate without depending on a centralized system. If those improvements happen, potential military applications become realistic. Logistics operations become possible, where robots carry ammunition and supplies across rough terrain to forward positions without human drivers exposed to fire. Urban navigation becomes practical, operating in cities and built environments where tracked vehicles struggle to maneuver. These are all genuinely valuable military functions. However, the timeline is important. Most military robotics experts assess that meaningful deployment of combat-capable humanoids is 10 or more years away. That's a long time. In 10 years, other technologies will have advanced substantially as well, and the comparative advantage may be different than it appears now. Military robotics experts also generally assess that current platforms are research grade. They're not designed with the reliability, durability, and long-term operational capability that military systems demand. If China were actively developing military humanoids specifically designed and hardened for combat roles, we would see different signals in what's made public. We would see hardened platforms engineered specifically to protect critical components, redundant systems for critical functions, so that losing one component doesn't disable the entire robot. Long-duration power systems specifically engineered for military endurance requirements rather than consumer demonstration endurance, and classified military testing programs that remain hidden from public view. Instead, what we see is public demonstrations of civilian platforms designed for research and industrial applications. This suggests that the focus is on commercial and industrial robotics, not military deployment. However, dual-use potential absolutely exists. Robots designed for factory automation or logistics could be adapted for military roles with engineering modifications. That's a genuinely long-term concern worth monitoring, but it's not an immediate threat that's going to change military balance in the next few years. Let's summarize what we actually know from the evidence. China demonstrated large-scale robot synchronization at the Temple of Heaven, with approximately 49 units performing complex choreography. Unitree Robotics shows significant production capability and has discussed aggressive shipment scaling targets into 2026. Balance and motion control in Unitree's platforms are advancing, and cluster control systems for coordinating multiple robots are mature and deployable. From a comparative assessment perspective, the West still leads in certain dimensions. Boston Dynamics' Atlas excels at autonomous mobility and unstructured environment navigation, making it capable of dealing with unexpected terrain and obstacles. Tesla's Optimus is advancing industrial autonomy and manufacturing deployment at scale within Tesla's own factories. Other Western companies are pushing the boundaries of what individual robots can accomplish and learn. These are harder problems technologically, and Western companies are pursuing them. China may lead in different dimensions. Scale of production is clearly one area where China has advantages, being able to manufacture more units annually than Western competitors. Unit cost efficiency is another, where manufacturing scale and supply chain advantages allow for lower per robot cost. Ability to coordinate multiple robots simultaneously while maintaining synchronization is demonstrated, as shown by the Temple performance. These are not small advantages. They matter for deployment scale and for how rapidly robotics can be integrated into industries. Military implications are long-term rather than immediate. War applications of humanoids are possible, but not imminent. Current platforms are not battlefield ready and would require substantial improvements before they could function in military roles. However, long-term dual-use potential exists if robots improve in the dimensions we discussed. And that's worth taking seriously even if the timeline is measured in years rather than months. The real competition in humanoid robotics isn't about who can make robots dance or who can put on the most impressive public demonstration. It's about who can manufacture intelligent machines at scale, integrate them into real-world systems, deploy them across industries, and iterate designs based on feedback and operational experience. China is optimizing for scale, manufacturing efficiency, and coordinated deployment. The West is optimizing for capability complexity and pushing the boundaries of what individual robots can accomplish. Both approaches matter. Both are advancing. The significance of the Temple of Heaven performance is not that it's militarily impressive or represents a fundamental breakthrough in artificial intelligence. It's that it demonstrates industrial maturity. When a company can synchronize 49 robots publicly without failures, it's a signal that manufacturing processes are stable, designs are validated, production capacity is real, and supply chains are working. That industrial capability is what shapes long-term geopolitical implications in robotics. Not dancing robots, not dramatic demonstrations, manufacturing capability, scale, and the ability to integrate technology into real systems.